First, just a brief presentation. Professor Rabitz graduated directly and got his PhD at Harvard. Now he works in Princeton, and his main areas of research are control of quantum phenomena and analysis of complex systems, working in the chemistry and applied mathematics department.
Thank you. I am truly delighted to be here, and I need to introduce my colleague Tak-san Ho, who's here as well. And we're just having a fantastic time, both enjoying a little slice of Brazil as well as, of course, seeing, my gosh, the diversity of research going on here just in your group is amazing. So I'd like to tell you a story. Can we turn this? Is it too dark? Is that all right? Okay. I'd like to tell you about this subject, and I think except for Emmanuel, I don't think you folks work with quantum systems, but the thinking of it in terms of control I don't think is active at this point here, but that's what we're here to discuss. So I'd like to tell you about this subject and how at least we think about it at Princeton and give you a slice of it, what the subject is about. And Vanderlei, as I said, and it's up to you, I would welcome doing this very informally and entertain questions along the way. Or you don't want to do that, either way.
It's your choice.
Okay, my choice is to entertain questions along the way, and don't be shy. We could spend 5 minutes talking about a view or something. We don't have to get all the way to the end either. So please, it's not interrupt. Please ask questions. So we'll see the significance of what this is a little bit later. And this is clearly a molecule, but think of it as a quantum system, and we're here to discuss the prospects that this might even be a quantum fluid. But it's a quantum system, and the game is to steer around quantum mechanics, engineer at the molecular or atomic scale, or maybe other related scales. This is what we call a photonic reagent. It interacts electrically. It's the electric field in the laser pulse. It interacts electrically with matter, and the matter interacts electrically as well amongst itself. It's natural to call it a photonic reagent. It's clearly a shaped object and has a broad spectrum. We'll talk about the need for that, and it's very different from this. This is monochromatic, this is not, and we need these crazy shapes, and how do we find them is a major issue in order to pull this off. Okay, that's what we're after. So I'll tell you just briefly a little bit about the history of the subject, how we find these things. I'll give you a list of what people are doing. There's labs in many places in the world doing this, and show you one experiment we did at Princeton, and then spend most of the time addressing why does this work at all. And there was many arguments that it wouldn't work. So that's what I'm going to do. And maybe a hint at the end, if we have time, about the beyond. Of course, the beyond is always where we like to be thinking about. So here's a succinct summary of the history of the subject. Nobody takes credit for the initial thoughts here, because I think when the laser came on the scene in the early 1960s, it occurred to many people in the sense that, if you can burn holes in razor blades, why not burn holes in molecules? And the thoughts were there. And originally this was thought of as a spectroscopy problem largely. That is, if you want, and in chemistry, it started with chemistry. If you wanted to break this chemical bond, well, take the spectrum of the molecule, find that frequency, get a laser at that frequency, and pump like heck. And for about 15 years, people tried that, didn't work. PR stands for photonic reagent, not public relations, incidentally. Things began to change in the late 1980s when this was recognized as really a control problem, and engineering principles were brought in, and then the right laboratory tools became available, and serious experiments started, as I'll tell you in a few minutes, in the late 1990s, and here we are. This is a whole subject on itself, but that's a brief history of this. So, regardless of the application, there's one principle behind this. Everything's linked to this principle. So we think of starting a quantum system in some state. It may not be a pure state. It could be a mixed state. It could be a thermal state. It could be a state described by a density matrix, not just a wave function. But the game is to steer it to some final state that we're interested in. And the assumption is the observable is maximized or extremized in some way in this state. This is a desired state. We want to go from here to there. And inevitably, there are many other places you can go. And so this problem becomes a challenge because we want to null out the other possibilities and maximize this one. And this is generally done by playing on constructive and destructive interferences. Quantum mechanics is a wave phenomena. So how do we do that? We go back to the laws of physics. And H naught is the Hamiltonian without any intervention, any control in the laboratory. And by definition, this doesn't happen to any reasonable degree, doing nothing. So we want to introduce a control, and it generally, in the optical case, looks like this, although it could have other forms. But there's a field, an unknown field at this point, coupled into the system, and the game is to find out what this looks like, or find it, such that this happens well. That's the objective. This is an inverse problem. We're sort of given the answer, what's the question? And why do we want to do it? As I said, the main reason that's been motivating this area for 60 years almost, 50 years, is to manage dynamical events at the atomic molecular scale. There are arguments that if we can do that, then we'd learn about fundamental subjects, fundamental dynamical issues, fundamental issues of the structure of the Hamiltonian. That so far, for the most part, hasn't happened. It's harder. The first thing to do is to get things under control, and then maybe we can go a step further. And then there's the issue of applications and technology transfer. People think seriously about this. That's a separate matter. Okay, so there's a principle behind it. Any questions about this? If you haven't asked anything, yep. Any questions? No. Yes, go ahead.
Could you perhaps give a concrete example of something that one would like to do in practice with one?
Okay, let me go.
Breaking a molecule. That's too vague, let's say.
That's too vague?
Yeah.
That's as concrete as we get.
That's as concrete as you get?
No, I mean, so indeed, this started with chemistry. So, I mean, I could draw a molecule, I'll go back. I mean, I'll be more specific in a minute with some real examples, but we can go back to this, and that's a cartoon. This is pointing here, and of course, the laser wavelength is much larger than the molecule itself, so you don't literally point at a bond. But the objective in something like, historically, the objective was in something like this was break this one, but don't break any of the others. And all of these problems have this type of character. Do this, but don't do that. And sometimes it's do this, but don't do that, and do it in minimal energy as well. So what happened in this area historically is it did start with chemistry. Chemists, physicists as well, thought about doing this in the chemical context. When this was finally evolved to a practical form in the late 1990s, and some experiments started, they did start in chemistry. But immediately, many people from all types of areas, including, for example, making high harmonics, controlling high harmonic generation, you name it. Think of your favorite quantum phenomena. If it exists and you can couple into it, in principle, you can control it. So what happened is many people in many different directions came in. All of a sudden, a huge list of things have blown out. So here we are to discuss maybe other applications in quantum fluids, which is an exciting frontier. So it's up to you to think about what to do, basically, okay? Other question? Okay. So how might we find this? That's the goal. In principle, we could treat it as a design problem, go to the computer, solve Schrodinger's equation, and search for this control. And it's a tremendous industry to do that. We do that a lot ourselves. The manual does that. Much of what we understand in a qualitative way about this subject has come from that, but the experiments, for the most part, 99% of them don't operate with those controls. They operate in a different way because we can't do the designs very reliably. So the apparatus, as a cartoon of the apparatus, looks like this, and I'll show you a real lab a little bit later, picture of a real lab a little bit later. The heart of it is the laser and the pulse shaper, and I think you folks probably are not too involved with pulse shaping, so I'll show you how that's done. But important point here is the laser has lots of keys on it. It's like a piano with lots of keys. They need to be set, played just the right way, you have a trial pulse shape, you apply it to a sample, and some sort of detector. It might be another probe, it might be an optical probe, or the sample might spit out a photon you detect, or a fragment might come off. Use a mass spectrometer. What the detector is depends on the application, but it of course needs to be sensitive to the state or product you're interested in. So the yellow highlights are here for a reason, in that a conventional experiment in any area is you set the knobs on the apparatus, you have a sample, you set the knobs in the apparatus, you do an observation, you go to dinner, you think about it, come back, reset the knobs, do another experiment. You could do that with this apparatus as well. But what's special here is the duty cycle of this. The rate that we can change these shapes is up to a million times a second, although none of the experiments operate that fast because of signal averaging. But it's realistic to say that we could do 10,000 independent experiments in the order of minutes. And so you throw out the capabilities of these machines by operating them in a standard way. And so no human being can, first of all, think fast enough in that time scale. And secondly, you have to think in hundreds of dimensions, which has to do with the hundreds of variables here. And it's not easy to think in hundreds of dimensions, so we get the human being completely out of the loop, other than setting up the machine, and replace the student by a learning algorithm. That's sort of how we think about students. There's a pattern recognition algorithm that's telling us we looked at the previous experiments, is suggesting a new one, how to set the laser pixels, if you like, on the pulse shaper, and around this goes to convergence, hopefully. So the quote at the bottom, I'll read it to you if you can't see in the back. It's from Peter Debye. Not in this context, but he said, you should understand the physics, which was the constructive-destructive interference story, write down Schrodinger's equation in this case, and let nature do the calculation. So this is a Schrodinger equation solving machine. Every time you want to solve Schrodinger's equation, you don't go to the computer, you do an experiment. That's really what's going on here, okay? Let me just emphasize something that may be relevant to some of the things you folks do. This issue of preparing a fresh sample, this type of experiment is distinguishable from experiments where one single quantum system is followed in real time. The experiments we do, anyway, now are on the pico and femtosecond time scale, and just for electronics reasons, mechanical reasons, you can't imagine, at least with current technology, keeping up with anything that's changing on that time scale is just not practical. So we throw the sample out each time and start with a new one, a new molecular or atomic scale sample. Whoops, yeah, I think that's right. So pulse shaping, how is it done? This is the raw pulse, and most of these experiments use the titanium sapphire laser, operates around 800 nanometers. There are exceptions to that, but there's a raw pulse, no shape to it. It's just sort of featureless Gaussian. That's the carrier wave. It's short, let's say 25, 30 femtoseconds, so it has bandwidth, and bandwidth is king. So what I was telling you before, in the old days of this area in the 1970s into the early 80s, people tried to use lasers like this, one color. And I think all of you have probably seen classical mechanical movies of molecules moving around. And if you look at those movies, some of the atoms move fast, some of them move slow. The motion is clearly very broadly spectral. And just from a classical point of view, if you're an engineer trying to control a mechanical object, let alone a quantum mechanical object, that has broad spectral character, you can't control it with one frequency. And the analogy that's good is trying to play a Beethoven sonata with one key on the piano. It's not going to work. But yet people persisted for 15 or 20 years trying to control very complex dynamical objects with one color, and it failed. So now bandwidth is king here. So we start with a short pulse. You can't pulse, you cannot shape in real time because it's too fast. So we shape in the frequency domain by Fourier transforming, having the pulse strike a grating, separate out the colors, and then you have a mask, some sort of electronically tunable mask. A common type is one made of large numbers of liquid crystals, although there's other variants of this. And as you can see here, some of the colors have come through and some of them have not. So that would be amplitude modulation. but we also frequently just phase modulate. So each color passes through, there's an tunable index of refraction. We can phase shift the colors relative to each other. Then you recombine the filtered spectrum on another grating and does the inverse transform, and within the original bandwidth you can make any shape you want. And the rate of duty, the duty cycle of this is the rapidity that you can change the pixels. Liquid crystals is about a kilohertz. There are faster ones than that. So this is a very inexpensive technology that grew up in the telecommunications industry originally for pulse shaping and optical fibers, but now it's exactly the technology used here, okay? So let me emphasize again, there's hundreds of these pixels, typically up to 1,000 now. Each one of them is, of course, digitized, but the number of gradations is about 50. So we have 50 settings for each pixel. Take a number like 500 of them. In principle, there's 50 to the 500th power number of shapes you can make. And rather a very prodigious number. So what's going on? You asked what's going on in this area. This is a list I made about 2 years ago, and it probably is not accurate. So what's on the left are the applications, and somewhere in here is chemistry. In fact, so there was a paper I gave to Vanderlei that we wrote a couple months ago where we surveyed all of the experiments. There's over 100 of them now, 125 or 30. If you look at the chemistry fraction, they're actually a minority. All kinds of things are happening. There's no order to this. There's atomic excitation and polyatomics and biomolecular energy transfer and decoherence mitigation, which is relevant to quantum information sciences, all kinds of things going on. And as I said before, it's up to your imagination. If you have a system and you can get a wrench in there, you can turn it. And that's what's going on here. And so think of it yourself. What's on the right side here are the actual sources of radiation. As I said, mostly these experiments are done directly with titanium sapphire pulses, sometimes very intense, 10 to the 14 or so watts per square centimeter, sometimes not. But sometimes the experiments are done with, off in other regions, or ultra broad bandwidth radiations used. And these sources have now been, this is what the cartoon is trying to show, this closed loop process. Some of these sources have been optimized under closed loop, and then those sources, in fact, applied over here for another closed loop. So both source generation and applications are both being done the way I was indicating, okay? So what's at the bottom here is a question I'll come to. As I said, I'd like to talk about this. And of course, the word easy is in quotes here. In some sense, it took 50 years to get here, so that's not a measure of easy. But there is a very quantitative measure I'll come to about why we use that word. Again, please stop me about any questions, okay? So I'd like to show you just one experiment we did recently. Recently, what does that mean? It took 5 years to do this experiment. It was published recently. And the experiment concerns the simultaneous control of multiple distinct quantum systems. So all of the experiments that I was showing you here, what I'm showing you now has to do with 5. The discrimination of very similar, it says molecules, but it could be, just say quantum systems. Everything else here is a sample of X. X is X, whatever it is. Whatever it is, it's the same thing. But the principle behind this is not restricted to that. And it's an interesting question if we have L, capital L quantum systems, and they don't see each other. They're distinct objects. They might be quantum dots or molecules. They're not interacting, but they're there in the sample. We apply a control field, a laser field, to the whole sample. Every quantum system sees the same laser field. And the question is, can you simultaneously manipulate all of them? And what the cartoons show are unit spheres representing the fact that each wave function is normalized. And the question is, in principle, Is it possible to manipulate points on these spheres freely for all systems? And there's a theoretical mathematical analysis you can do based on what's called controllability theory, and it says in principle that if these quantum systems even infinitesimally differ from each other, that in principle you can arbitrarily manipulate all of them. It doesn't tell you the resource you need. And maybe the resource you need is not easily attainable in the laboratory, but it's an in principle statement. Armed with that, it's interesting to ask, how far can one push this? And we don't fully know the answer to that. But the experiment I'll just show you, I think, pushes it pretty far. So in principle, this can work. So I'm sorry about how hard this is to read in the back, and gosh, it's pretty bad. So we call this process optimal dynamic discrimination. So we have, in this case, two molecules. They're biologically relevant molecules. One is riboflavin, the other is flavin mononucleotide. Everybody has them inside of them. They have very important biological functions, but that isn't the reason we did the experiment particularly. Optimal dynamic discrimination is if we have these two very similar molecules in a sample, can we discriminate them optimally to do the best we can, make the best use of resources, and dynamically. This is a quantum dynamics process. So I'll have to just kind of read this for you because, gosh, if your eyes are like mine, it's not very visible. So there's a triple ring structure here, fused rings involving carbon and nitrogen atoms. And there's a tail hanging off. The tail is, I don't know, about 6 carbon atoms long. And at the end of the tail is X. For riboflavin, X is simply a hydrogen atom. And for flavin mononucleotide, it's a phosphate. They don't differ much. Biologically, they have very different functionality. But if you go in the laboratory in a test tube and look at these things, by ordinary spectroscopy, they look the same, or almost the same. And what I'm going to tell you here, I'm sorry you cannot see it, is the absorption spectrum and the visible in UV. It has some diffuse structure, but no discriminating clear features. And the spectra within the width of a pencil line is the same for these two molecules. It's in water solution. It's because it's primarily due to the ring structure, electronic vibronic excitation in the ring structure. And the ring structure is common to both species. The emission spectrum is centered around 500, 550 nanometers, and once again, within the width of a pencil line, they're the same. So nobody rationally would try to detect the presence of one versus another by ordinary spectroscopy means. So the question we asked is, can we do this dynamically? Hit them over the head with a fast hammer, but a hammer that's shaped just the right way, such that we can pull the signatures apart. So theory says in principle you can do it. In practice, do we have the resources? So what's shown here is a very oversimplified cartoon of the electronic vibronic structure of these molecules. They're very complicated, but it captures the essence of what we did. So we shaped a 400 nanometer pulse. It came from doubling the 800 nanometers in a nonlinear crystal. We shaped this pulse, did phase modulation on this pulse, and then we monitor a fluorescent signal. It comes out about a nanosecond later, which is infinity on this time scale. So by the time the fluorescent signal comes out of either molecule, the excitation created in this excited vibronic state is decohered, vibrationally decohered. There's no quantum coherence by the time we record the signal. So if we shape this pulse and monitor the fluorescent signal, we have two samples, one with RBF, one with FMN. They both are seeing the same pulse coming in. If we do that, shape all you want, the fluorescent signal is identical. You can't discriminate that way because the coherence is lost in a nanosecond. So what we did is we operated this closed-loop machine that's learning how to shape this, but not alone, but in the presence of an 800 nanometer pulse that was time delayed from the 400 shape pulse by about 250 femtoseconds. So the blue shape pulse is creating some kind of vibrational excitation in this complicated ring structure up here. We asked that the 800, the point of the 800 pulse is it takes some of that excitation up to higher excited states and it never returns. And it depresses the fluorescent signal. It depletes the signal. And what we're asking to happen, there's no guarantee we could do this, but I wouldn't be telling you if it didn't work. We're asking that the degree of depletion be different for the two molecules. Well, how might that happen? The degree of depletion is very sensitive to exactly the vibrational wave packet structure at 250 femtoseconds after its creation. And we're asking the closed loop apparatus to learn how to pull those wave functions apart in the two molecules such that we get a differential change in this fluorescence signal, and it does work. So what's shown over here is the ratio of the signals from the two species. One is the ratio is 1. There's nothing. That occurs with the cases where you don't apply the red pulse or you don't shape this one. And that's just like ordinary spectroscopy. You can't tell the difference between them. But we ran an experiment that says drive up the ratio or drive it down. The scale here is about 20% up, 20% down, which is dramatic. These spectral curves are less than 1% away from each other, so this made a huge amplification of the distinction. So this experiment shows, in some sense, the capability of making two things that by ordinary means look similar to each other look now different. And there are also illustrations where you can make different things look similar. And so when you get into this domain of quantum control, and this is a nonlinear process because of the two colors involved, if we can make similar things look different and different things look similar, then we've lost our intuition, at least for now. And this is why the field is sort of blossomed out quickly. In principle, there's all kinds of things one can do. Okay? Any questions about this?
Not about this, but do you know any experiment about quantum dots, involving quantum dots?
There are some experiments. We haven't really done them, but there are some experiments.
Not about assembling, but about coherence?
Yeah, but coherence. Coherence. There have been done some coherence. Taxan, do you know about any or not? I'm almost certain there are.
Okay.
Other questions? Okay. Okay, so it works, at least to some degree. So this brings us to this question. And it occupies a lot of our time wrestling with this. So this is the cartoon I showed you before. And what I mean by easy is not the time it takes, which the Flavin experiment took 5 years. Over 3 years of it were to stabilize the laser system, doing engineering that we should not have had to do, but the lasers that come out of these companies, at least when we bought that system, were lousy. And we demand very high quality phase stability, and they were telling us, great, shot-to-shot energy stability was to 0.5%, but the phase stability was all over the place, so we had to wrestle with that. So I'm not talking about the overhead of how much time it takes to raise the money, or how much time it takes to set up the experiment. How much time it takes to do any of that overhead is not the issue. What counts is, and that was true in the Flavin experiment, it took 5 years, but the last 20 minutes of that experiment is what counted, because when we pushed the button finally, it took 20 minutes for it to home in on the target. And remember what I said, and this spoke to a problem that people said would not work. So we have that particular experiment, there was about 100 pixels, but all right, use 500, that's the typical number these days. We had 500 pixels, 50 settings each. As I said, it's true. That is, we could do 50 to the 500th power experiments. And if you look at that list I showed you, if you actually look at in these experiments, many people report how many iterations they did around this loop. And if you look at all of it, the 100 and some experiments, a rather shocking number jumps out at this. It doesn't matter whether you're trying to control an atom or some complicated biologically relevant molecule, it always takes the same number of experiments, and that's a number of roughly 1,000 to 10,000 experiments, and that's the order of minutes to an hour. Sounds like a large number, but it's not compared to 50 to the 500th power. And that really leaves a puzzle here. And many people argued about 15 years ago, before these experiments were ever tried, that this wouldn't work because one searching in a very high dimensional space for a needle in a haystack, and here we're left with this puzzle. Not only does one beat that, which is called the curse of dimensionality in mathematics. It doesn't seem to matter how complex the system is to boot as to how many iterations it takes. And we,
Question.
yes?
What kind of adaptive algorithm do you use? Genetic algorithms?
So most of the experiments, in fact, do use genetic or stochastic-based algorithms. But we also now use deterministic algorithms because there's something, pardon?
Direct search?
Well, I don't know what the word direct search means. A local algorithm would be one where you make one step and look one step forward. So a gradient algorithm would be an example of that. So, well, as a side comment, so getting at this issue of why does this work, so there's the laboratory side. And out of the 125 experiments have been done, I'd say 123 of them have been done with stochastic algorithms. It's only in the last 2 years that we did some experiments at Princeton with gradient-based algorithms because a principle began to emerge here that said those should work as well as the stochastic algorithms.
Is that the case?
It is true. In some cases, they even beat the stochastic algorithms. But there's a fundamental principle involved. Now, if you, pardon?
That is puzzling.
Pardon?
I think that's puzzling.
Well, exactly. It's puzzling, precisely. And so the flip side of this, I don't show it here, but the simulations that I said are not used to design the laser pulses are still in the literature. And there's 1,000 of them, I'd say, roughly speaking, many of which we've done, and manuals doing them too. And if you look at that literature, almost none of those are done with stochastic algorithms because stochastic algorithms are expensive to do on the computer. Experiments are cheap. We can do an experiment in a blink of an eye, but to run computer simulations here is expensive. So almost all of these computer simulations are done with gradient algorithms. Now, if you look at that collective literature, the shocking thing that jumps off the page there of the 1,000 runs, everybody gets better than 90% yield. Everybody's results, no matter what they're looking at, it's always above 90% yield with a local algorithm, invariably. And indeed, there's a puzzle here. Even though those designs are not real with regard to the laboratory and the computer, they're perfectly real in terms of the computer simulation, quantum system. So something odd is happening here about this. And this struck us about 5 years ago, 6 years ago. Something screwy is taking place here. We do not understand all of it, but we understand the basic parts of this. And that's the story I wanted to tell you.
Sounds like an anti-Murphy law.
Pardon?
Sounds like an anti-Murphy law.
Murphy.
I know Murphy's law, but what?
What's the reverse of that?
The inverse Murphy's law. Well, right. It's, you know who Leibniz was? He was quoted as saying, some people make a sarcastic comment about it, but it's the best of all worlds. And you'll see there's something about this that says, God, life couldn't be better than this. So what's behind this? So first of all, this looks like, I now see some of your labs too. This is a third of our lab. We have 3 laser systems like this, and of course there's tremendous overhead in setting this type of stuff up. Again, this is not what I'm talking about. All that overhead is irrelevant with regard to when you push the button. So a typical talk that you used to hear a few years ago, someone would come and whatever the experiment is, and they would make this comment. They could do 10 to the 400th power or whatever number they picked, number of pulse shapes, and some people would be wowed by that. And then 3 sentences later, they tell you the experiment worked well, and they did it in 2,500 iterations. And you look around the room, no one seemed to be bothered by this comment. But you know, it's a shocking statement that you can do an infinitesimal search in a high-dimensional space, and repeatedly so, and win. So why is that is the issue. It's easy as not this picture. So one perspective here is to go back to, of course, Schrodinger's equation. Everything lies in Schrodinger's equation. The answer to everything. Let me remind you, the question we're after in this context is not what dictates exactly the shape of that laser field. That's very sensitive to the details of the Hamiltonian. We're after why does this repeatedly work? So the answer to that must have something invariant. The answer must be invariant to the details here. The fact is, we don't know the Hamiltonian of real systems very well, except hydrogen, or maybe sodium. We don't know it in detail. L is very large in many cases. Many particles are involved. Mechanism lies in here. We don't really fully understand this. But it doesn't address the question. The question was, why does it work? So there's kind of a blue-collar worker's perspective, not like my white shirt here. You go into the lab, you turn the knobs, and the 300 or 500 pixels, you turn them, and you see a response. You go back and turn them again, you see a response. That's what's going on in the lab, as well as on the computer in simulations. So it's not the energy landscape, this function which looks like the Alps or the Himalayas, or what is the mountains over here, the Andes, I guess, in 300 dimensions. This landscape looks terrible, very rugged. The question is, what does this landscape look like? Because this is what counts. And the crux of what one can show, and this is what I would like to do for a good part of the rest of the talk, is you can prove, and I mean that word carefully, that the topology of this landscape, which is really what we're doing in the lab, we're climbing up this landscape in the lab, the topology of this landscape is completely generic and has nothing to do with what particular quantum system we have. And secondly, it does not look like the Andes in 300 dimensions. It has no traps. There are no low hills to get stuck on. And so this result qualitatively explains why these experiments work. We don't understand every aspect of this, and we don't understand all the consequences of it at this point, too. There's an interesting historical comment that is not fully understood, and I don't know the full history here either, but there's a paper by von Neumann in 1937 where he went through some mathematics, and he was developing quantum mechanics at the time. The paper doesn't even mention the word quantum mechanics, but if you actually looked at the paper, you'd recognize quantum mechanics in it. And the mathematics he went through is very related to the mathematics of proving this point. And the hint, but no one has really looked at the historical record carefully as far as I know, is von Neumann very likely thought about controlling quantum phenomena. There were no lasers and no means of doing it at the time, but he took a mathematical stab at it to show the principle behind this, and I don't know whether he really did it or not. We don't know, but there's a hint there. Excuse me. Yeah. Excuse me.
What do you mean by local, by traps?
Okay, so a trap, okay, here we are. This, good, perfect timing, Emmanuel.
Okay.
So here's the picture I showed you at the beginning. Here's the hiker. So this would be the gradient algorithm. He's got a stick, a blind man with a stick, trying, and this is 2 dimensions. So in the laboratory, we're marching through 300, actually infinite dimensions, truthfully, but 300 discretized dimensions. That would be a trap right here. It's a low hill with a peak. And if you had a gradient algorithm and you were a hill climbing algorithm, you'd climb to the height of that and you'd say you're through. You would never know that, in fact, this or that is the highest peak, and you'd never have a way of getting there. Now, in principle, these stochastic algorithms can hop around, but the truth is, if you're searching for an extremum like this in 400 dimensions, there are no algorithms that can efficiently do that, truthfully. So what I'm telling you, I just told you this, and I'm telling you again, this picture is not what quantum control landscapes look like. They don't look this way. And one can prove that they don't look like this, at least under some conditions, okay?
So in your view, the landscape looks more like what? A hill that you're going up? There are some little bumps, but nothing like small.
Well, that's
You can't see it.
You can't see it. And one of our dreams here is, you know, we want to make a quantum mechanical rover. The word rover is an analogy with the little machine on Mars that's crawling along semi-autonomously to run over these landscapes in the laboratory and report back. So one picture, it looks like what you said. It looks like Mount Fuji. You know, you climb up. I'll show you some real landscapes in the lab, what we can see, at least in some cases. But generally, it's more complicated than that. And there's a distinction between extremum, measurements of extrema, like these little low hills. Extrema is a low hill or a saddle or the absolute top or the absolute bottom. Everything else that is not whose gradient isn't 0 in all directions is not an extremum, it's a feature. So here we are in very high dimensions, infinite dimensions. We can codify what the extrema look like and how many they are generically, but we know nothing about other features except empirically some information about it at this point. So that's possible, and lots of other things are possible at this point. We don't know for sure.
Sure.
Yeah.
The energy landscape, you have the energy as a function of the process, right? I understand that.
Right.
But what is the control landscape?
It is not the energy landscape. So this variable down here and that one over there are knobs, two-phase pixels, 2 pixels on a pole shaper.
The height is the accuracy.
It's yield. Okay, it's the yield of what you're trying to create, the amplitude in the product.
But how do you measure? I mean, do you have you would need a generic definition of
So we used, for example, as I'll show you in a moment, trace rho O, trace of the density matrix times observable, which is a general observable in quantum mechanics. But it, what that actual signal is depends on the experiment. It could be the fluorescence intensity, or
Because of course, when you see the trace of,
Okay.
you're going to write it down?
yeah, I'll write it down for you. Okay. Okay. Other questions?
So, but just to complement that,
Sure.
you're saying that it seems that what matters is not what intuitively you would think, it's just the energy landscape, the Hamiltonian
Right.
solution of the Hamiltonian. But the control landscape, that is sort of a combination of whatever output you want.
That's
with
correct.
With the control parameters, that it's
Right.
slightly less complicated. somewhat.
That's correct. And generic. I mean, it's shocking that there's anything generic in this. The laser pulse shapes are not generic. They're highly specific to the Hamiltonian. The Hamiltonian plays a role in the back. So the answer to this had to be something generic. I mean, the evidence was there. There was something general going on that did not depend on this. Now, I must tell you, we didn't look at it this way. It took us a long time to come to this conclusion. It did, it sounds easy at this point, but it didn't come this way. The detailed structure of the Hamiltonian enters only one way, other than finding the control itself. It enters in establishing whether in principle there's a pathway between where you start and where you finish. That's all it does. It's an in principle statement. And there's a statistical argument that if you go to the stockroom and pull virtually any bottle off the shelf, the chances of it not having a pathway from any one point to another are zip. It's not going to happen. So there's always going to be at least some screwball pathway between where you are and where you want to go. That shoves the Hamiltonian, it's gone. It, of course, reappears when you go into the laboratory and search for the control, but not in terms of this issue of climbing. As soon as that principle's gone, we're back to looking at the generic structure of this. Okay? Okay, how do we do this? So let's just walk through some of it and see where we're going. So this is the observable. We pick a target time. It might be finite, it might be infinite or asymptotic. The trace of the density matrix at the target time times the observable operator is a general observable in quantum mechanics. And rho at the target time is the full time evolved evolution of the initial density matrix. And U satisfies Schrodinger's equation here. Full Schrodinger equation. We assume something, I just said this. We assume that the system is controllable. And statistically, that's a sure bet. The system Hilbert space is taken as dimension n. There's a subtlety there, I think a very minor issue generally. N can be anything. It needs to be finite, though. It might be 10 to the 18 or 2, but it's finite. It's not infinite. That's not, I think, an important issue. That's enough. And so to get the entree to how to prove this statement. So there's just a restatement. The landscape is this observable as a function of the control. I mean, technically, it's a function Al, because the field enters Schrodinger's equation as a function, and the observable is an integral of that in some fashion. The field enters through U. We do not understand this mapping. It's generally highly nonlinear because of the nonlinear nature of the experiments, but it exists. So at this point, you might stop and say, well, this is hopeless. We can't really understand this, but it turns out, if you ask the right question, you can. So what we're after, we want to take the derivative of the height on that picture I was showing you, which is L. with respect to the field and set the derivative equal to 0 for all time. 0 to capital T. That will, if the satisfaction of this equation will identify what's called a critical point. It's some point in control space. It corresponds to some field where we're at the top or at some extremum in the landscape. And the question is, what are the values of those extrema? And we want to determine if they are minima, local minima, maxima, absolute minima, or saddles. What is their character? We also would like to determine a bound on this slope. This is the gradient. If the slopes can be like this, we're in trouble in the lab. I mean, of course, the evidence is they don't look like this. Why? If the slopes are bounded by physical reasons, we're in good shape. We're not going to try to climb this up because in the lab, there's noise. You'll never be able to climb something that's too steep. So we want to find the critical points, their values, their character, as it's called, and bounds on the slope and curvature. And we want to know, what does it look like at the top? How flat is it at the top? It's very important practically. So I could skip this, or I could walk through this. This is taken from a paper of Taxon's, and it really is linear algebra that leads to this conclusion. How much time do we have here? How much time do we have here? I don't know when we started, actually.
Well, officially 15 minutes.
Officially 15 minutes?
Extra-officially, half an hour.
Okay. Okay. So let me just walk through it quickly. And you want to see the details, we've published this. So there's L again, the landscapes, the functional control. We take the derivative. It's a page of algebra, operator algebra. You find the following expression. It's the trace of a commutator between the initial density matrix and the target, or evolved to the full, under full evolution to the target time. This is time independent times a matrix, which is the full time evolved dipole matrix.
What's the difference between capital T and small t?
So capital T is the target time, small t is the running time index that goes from 0 to capital T. So this derivative is asked to be 0 for all little t, up to capital T. Capital T may be infinity in some problems, but usually something finite, okay? So the way you look at this is, we have this demanded to be equal to 0 for all t. This is time independent. A reasonable assumption is that this matrix is full of elements that are linearly independent of each other. Think of the time evolution operator, how complicated it is. So if we take that statement, which is related to the controllability assumption, accept it, the only way this can be 0 for all time is that the constant coefficients are equal to 0 independently. So we come to this very simple, stark statement, no Hamiltonian in it at all at this point, that the initial density matrix commutes with the observable at the target time. So if you have two Hermitian operators that simultaneously commute, that means there's a unitary transformation, V, which will simultaneously diagonalize them. So there's a transformation V which will diagonalize the initial density matrix and produce these eigenvalues, and will diagonalize O at the capital T and also produce its eigenvalues. So if we take this equation, O of t, and just plug it right in here, just drop it in, you get this equation. You can see U adjoint O0U, that's this thing here, and then V adjoint V sandwiched around is equal to sigma t. So all I did was plug this into that. Now O0 is here. O0 is a Hermitian matrix as well, and it can be diagonalized. The transformation that does that, I call it X, and I wrote the eigenvalues on this side. So this is diagonal, and there's the unitary transformation. There's O0 because I want to plug it in here. So I just substitute this into there, and we get this relation where you'll note if we plug this in here, there'll be X adjoint UV, X adjoint UV, which is pi. It's the product of three unitary transformations, and the other side is pi adjoint. Excuse me. This is a very curious mathematical statement because sigma t is a diagonal matrix. Sigma 0 is a diagonal matrix. we have two diagonal matrices related by a unitary transformation. How can that possibly be? Two diagonal matrices related by a unitary transformation. The only way that can be is if pi is a permutation matrix. That we conclude very generally that pi can do nothing but permute the eigenvalues around. That tells us that up to a unitary transformation x and v, you go through all this quantum mechanics on the computer or in the laboratory, what you generate is a permutation matrix. That's it. What's going on with a control field, it's finally creating a permutation matrix. So what's the consequence of that? In fact, well, let's go to that. So I've restated this by putting u over here and putting the pi and x and v adjoint on the other side, where this is what x and v did. What this tells you, and there's a couple lines of algebra that comes from this, is we found the critical points, and you can now go back to trace row O and show that all the critical values range from the eigenvalues of the observable operator and the eigenvalues of the density matrix lined up in parallel from highest to lowest, which is the highest value you can get, all the way to anti-parallel, which is the lowest value, and every possible permutation in between. We have n states. How many permutations are there? There's n factorial. So that tells us that this landscape, you have to shut your eyes, you're in infinite dimensions or 300 dimensions. It's got n factorial critical points in it. So far, we don't know whether they're traps, saddles, or what they are, but it's got a factorial number of them. The ideal experiment in the laboratory, at least one can think about, and most of the computer calculations start really simple. The idea is you start in a pure state, and you go to another pure state, state to state. So most, 95% of the computer simulations are calculating the probability of going from one state to another. Experiments would like to do this, but the lab's a little messier. But this case is a good prototypical case because the eigenvalues of rho are all 0 except one of them, which is 1. And the eigenvalues of O, we know immediately, are all 0 except one of them is 1. You come back to this formula, the right side is 1, and the only non-zero value on the lower end is 0. And so for this very clean picture of going from one state to another, the landscape, in fact, has nothing but a top and a bottom. There's no saddles, there's no traps, there's nothing at all in between. Now, I'm just going to tell you this.
You had n factorial and I have 1, 2?
That's correct. And there's up to n factorial. Up to. And the number you actually get depends on the eigenvalue structure of the observable.
No, you have a lot of them on the same height, isn't it?
Well, in some sense you could say that. In fact, there's a huge degeneracy of solutions. I don't like to count them that way, but because we're going from, we're counting discrete numbers of things here. So if you have a initial density matrix which is full rank, in other words, it has n non-zero eigenvalues, and an observable operator which is full rank, it has n non-zero eigenvalues, you'll get n factorial. The number of critical points drops as the number of those eigenvalues, non-zero eigenvalues drop. Finally, you get down to pure state to pure state, and there's nothing in between. They keep dropping.
But it's the values, only two values, not 2 points.
They're two values, not
Values, yeah, so you can still have n factorial critical points.
no. There are only 2 critical points. The critical points where the derivative is 0. For state to state, there's only 2 critical points, the top and the bottom, 0 and 1, nothing else. The number of critical points, I mean, the n factorial is a little misleading. That's as much as it could be. It's the highest limit it could be. The exact number depends on how many distinct things we're permuting around, distinct non-zero eigenvalues we're permuting around. With pure states,
So the curly L in the formula is the number of critical points.
it's the value of them.
Value.
Right.
So you have 2 values, but you could have many critical points. Or-
There are not, though. You could, but it doesn't happen.
But it's a different proof. It's not this.
No, it is this proof.
Oh,
There-
it is this proof.
It is this proof. There are no others. Okay, there's a corollary with this we'll get to quickly. At the top, there's an infinite number of solutions. The top is not a point. It's not a single point, but it is, the value is fixed. It's 1 in this case. But there's an infinite, there's a level set at the top. There's a
So
continuum.
you're
of-
saying every time two critical points have the same value, they must be the same point?
No, they are, what you do is we have time, I can show you an experiment. So you can drive up to the top of the landscape, climb up by some algorithm, turn right and drive across the top. There's a level set at the top, a huge level set. And you can drive across. Every point on the top is a different control solution, and they're continuously morphable from one to another. There's an infinite, if there's a solution to these problems, there's an infinite number of solutions. There's not just one
So
solution.
that is equivalent to infinite number of points.
Well, but
Yeah, so
it's
But they're not far apart.
they're next to each other.
They're from a continuum.
Each
continuum.
one corresponding to a different solution.
They're different.
So in that in the same, they are different points. Yeah, but they of the same values. Yeah. So in a way.
And they are
yeah,
infinitesimally next to each other. This is very non-trivial. I don't see that.
No, you can't see that from here. Okay. But you cannot see that from here. You have to look at the Hessian. So you need to, all right, you drive up to the top, first derivative, 0. It does not show from this. And then you have to look at the second derivative. And I'll tell you the answer here. Derive this is another couple pages of algebra. But you can show that the Hessian, which is the second derivative, first of all, it's an infinite dimensional matrix, either in the time domain or the frequency domain, because time and frequency are continuous indices here. So this is an infinite dimensional matrix, and you can show that if you have n states, we said we had an n state system, a countable number of states, that the Hessian is finite rank. In fact, it has no more than roughly n squared functions. These are matrix elements of the full-time real and imaginary parts of the full-time evolved dipole. What does that mean? You climb up to the top, and think of it as Mount Fuji if you want to, and you measure the Hessian or calculate it on the computer for simulation. You diagonalize it. The number of non-zero eigenvalues tells you the number of ways off the top. The eigenvectors tell you exactly the path, the associated eigenvectors tell you the pathway through the space off. Because the Hessian is finite rank and is always finite rank, but the matrix is infinitely large, that immediately tells you something extremely important. It says there's an infinite dimensional null space at the top. And when you have this, it tells you something very important in practice in the laboratory that people said was going to stop these experiments from working. That is, it says you go to the top and you have noise in the controls. Most of the noise goes down the garbage can into the null space. You're overwhelmed by a null space at the top, and there's only a few ways off. And that says there's an inherent degree of robustness to these problems because of this. Okay, so you have to really look at the details of this. You can't see it from the first derivative. And also, it doesn't show it here, but there's a prediction of what the bottom of the landscape looks like as well. Okay? I mean,
Okay, let me see if I
Sure.
understand. Because you have this finite number of paths that you can lead the top with, likewise.
Mhm.
Those, I think, are sort of the directions that your algorithm would take.
or some combination thereof.
Or some combination that your algorithm would follow.
Correct.
But has it taken one of these directions? It doesn't guarantee that that is the optimal solution. It's just one of them.
No, I suppose there's 10 of them.
Okay.
Any one of them or any linear combination of them will take you to the top or different points on the top. Okay, so a solution is a solution. If you looked at other characteristics of those solutions, you may be happy with one versus another, but that's not what was asked here. So there's generally an infinite number of solutions, and from an eigenvector point of view, a finite countable number of paths, although you could take combinations of them as well. Now,
Sorry to keep interrupting you.
Sure.
but I feel that this is the heart of the matter.
It is.
You just said there are a very large number of solutions, no? But you still maintain there is only one peak?
That's correct. So you go to the top. You can even see this in think of it a two-dimensional space, although I'll show you an example. So you could drive up. The top's flat.
The top is flat.
Flat.
And there's only one such top. Or do you have another?
All right. The full answer to that is not completely understood. but we believe there in fact are multiple disconnected
Flat tops.
flat tops.
Okay.
One world here, they're connected if you come back down, because everything's continuous. There are some cases we can argue through, under certain approximations, dynamical approximations, that are disconnected worlds. Proving this is not an easy thing, but generally we believe there are multiple disconnected solutions. But typically what we do, and we've begun to do this in the laboratory, I can show you an experiment that shows the basics of it, but we certainly do it on the computer. We drive up, turn right, and you can drive a long ways continuously, take trajectories along the top.
Flat tops is certainly much smaller than factorial n.
We don't know. I can give you an example.
You believe there are.
The number of flat tops has nothing to do with factorial n or anything directly to do with n, I believe.
It has to be a small number otherwise.
Why? Why?
Because your algorithm could be.
But it's an infinite, no.
It starts to climb the first flat top, and then it's driven to the other flat top.
Okay, so you end up someplace. So there's a
It
bifurcation.
can take much longer than 1,000 iterations.
Well, all right, that's another question, okay? How efficient things are, I'll just tell you this. So in the laboratory, we've done experiments, and I'm happy to take another hour to go through all this if you guys want to do this. I would spend all day doing this, but so we go in the lab. We also looked at this on computer simulations. So in a typical experiment, you make a random guess for a field. That's how the experiments work. We don't have any designs typically. So that's throwing a dart into this 300-dimensional space. You climb up, do 1,000 iterations or whatever. You can measure, because we have the field as we're climbing up, we can measure the path length it took through the 300-dimensional space. Just measure it or calculate on the computer in a simulation. We know where we started, we know where we ended up. Take the ratio of the path length to the Euclidean distance. What's that ratio? What we see in simulations and what we see in the lab, the ratios are very small numbers. They're like 2, 10. It doesn't look like this. And what we see is, if you start with a even half reasonable guesstimate for the field, in other words, the field at least has sort of the right spectral components for the problem, you look up, you can't take a straight line to the solution. It's twisted, but you can see skylight no matter where you start. And this has to do with the structure of the landscape, not the topology of the landscape. We know that the topology has no traps. If there were traps, we'd be dead. We wouldn't make it. So what we're seeing is, I mean, the best of all worlds here. You start anywhere, you look up, it's a short pathway to a solution above you. That solution has an infinite number of solutions in its neighborhood as well, which have different characteristics. You could climb different ways and land up there and maybe slide along. You could go over, you start over there, you don't tend to climb up to a solution over here. You tend to climb up to one over there. I mean, it's rather shocking that this is true, but that's what we see. Okay? Other questions? Yes?
Actually, there's a thing that I don't understand, because once you're on the top, that's because you got to the stage you wanted.
Pardon?
Once you're at the top, that's why you're at the stage you wanted initially. But what it means to be in different tops, you don't know now, because you are in the same state.
It's the same state.
Why should be, because one top that has a lot of solutions, so there's a lot, we imagine the pulses, there's a lot of pulses to get there. Okay, but what should be these different tops?
Okay, each point on the top itself is a pulse. A point on the landscape is the value, a point on the landscape corresponds to an entire control field.
Okay.
This is not a dynamical thing. The dynamics are hidden. There's not a potential energy surface. So you have a value of the observable. You're sitting at this point in the landscape. That's a field in 400 dimensions. It's a point. You go to the top, every point on the top is a field. And at least the solutions in this neighborhood are continuously morphable from one to another. Each point is a different solution.
When you
connected
It's
at the
connected.
top.
Okay.
At the top.
You don't change this maybe.
So what happens is if you do the following, and we do this, we have not fully done this in the lab at this point. We're very close to doing it though, but we certainly do it on the computer. We drive up to the top, and in the computer you can get machine precision. I mean really machine precision, in many decimal places you want. You climb up to the top, turn right. When I say turn right, what we do is we calculate the Hessian, or in the laboratory you measure it. I have a demonstration of that. You calculate the Hessian. You take the eigenvectors of that, and the eigenvalue, you take the eigenvectors with 0 eigenvalues, and you project the control field into that subspace that corresponds to 0 eigenvalues. So if you turn the control field components, and they're only allowed to project into the eigenvalues, or eigenvectors of 0 eigenvalue, they won't change the observable value. And you move in that direction. There's an infinite number of directions you can move. So here we are in an infinite dimensional space. And most you can do is take trajectories in an infinite dimensional space. You can ad nauseum take trajectories, but that's all you can do. But what happens is if you drive along, and again, you have to close your eyes. I can't tell you what it looks like either. We're in 300 dimensions. You drive along, you pick some direction. You drive along, and it goes for a while, and it stops. Because we asked to stay on the top. What happens is it hit a boundary. And if you try to go further, it'll take you off. And when the algorithm's a differential equation. Literally, it's following along the top. You come to a wall, it says, if you want to continue going, you're going to come off. And we said, don't come off, so you just walk. You stop. You back up, tell it to go in some other direction, and it wanders off, and eventually it comes to another stop. And so what we'd love to do is have an automated rover in the laboratory that will run around and start telling us what the heck we're seeing here. We don't know. I mean, it could be highly convoluted and complicated, but it's shocking that this stuff exists, really. You know, we were very surprised at this, too.
The top is flat. Once you found a control that takes you to the state you want, you can then change it continuously and still reach the same state every time.
Right. Now, when I say state, let's be careful here. We're not actually observable. I mean, actually going for the state is not an observable quantity itself. We're asking for some observable quantity, yes.
Still that's surprising.
It's very surprising. Very surprising. So you folks want to hear more, I'm happy to tell you about it. I mean, some of the stuff I have to show addresses exactly the questions you're talking about. So this is a statement, and I'll just quickly go through this here. There's the expression I told you about the gradient. It's the same thing I gave you before. Mu t is the full-time evolved density, full-time evolved dipole. The bound of this is just an operator bound, and it's just bounded by the norm of the observable times the norm of the dipole. And in any reasonable physical problem, the dipole has a finite value, and so does the observable. This statement immediately says the slopes are gentle. We're not going to see this, and of course that's consistent in the laboratory, what we see in the laboratory. You can also prove that the sum of the eigenvalues, you go up to the top, you add up all the eigenvalues, they're negative because you're at the top, the curvature's down. You add up all the eigenvalues, there's a lower bound on them, that sum, which is likely physically bounded once again. This makes a prediction, a very strong prediction, that as the dimension rises, the Hilbert space dimension rises, any given eigenvalue on the average is probably going to get smaller. In other words, the top gets flatter and flatter as the system gets more complicated. What's the evidence that's true in the laboratory? The best you can say in the laboratory, there's not one bit of evidence that controlling an atom or controlling biological molecules is any harder than controlling an atom. People had argued that, well, maybe we could control an atom or a diatomic, but my gosh, noise was going to kill us. This argues that there's an inherent degree of robustness to these problems. In fact, it argues that it gets better as the system gets more complex.
So the curse of the dimensionality seems to be a gift after all.
It's the best of all worlds. In fact, it's a gift. It's amazing that this is true.
Because the higher dimensionality, more likely
Dimension's your friend here.
to have a connection to whatever state.
It also says, and I'll make this an experimental point here, the constraints on the controls. You know, people are afraid of high dimensions in the laboratory in any area, not just this area. People like to say, get me down to 3 variables, I'll be happy. The argument here is you're making a serious mistake by doing that, because you'll end up taking some forced trajectory across the landscape and see false traps.
Okay, so is it correct to conclude that this is a feature of quantum mechanics? I mean, it doesn't seem to behave like that in a classical world. It seems to be
Okay.
simply the underlying mathematical structure of the
Okay,
problem.
it's a very good question. So the proof here was strictly based on quantum mechanics. We can prove this several ways. And we have been very interested in the question you raise as to whether there's a crash in this when you come to the classical limit, which would be a very disturbing statement, actually. You can't prove anything classically from this argument. But let me go back to something, and you can see the basis of it right here. No, excuse me. Here. Trace row O is, of course, you accept quantum mechanics, there it is. If you don't accept quantum mechanics, then don't swallow it. But it's a postulate of quantum mechanics. But this has a classical analog that was known, prehistorically. If you wrote down, if we had a classical observable and there's a probability measure for it, the integral of that over the phase space is a classical observable. In fact, it looks just like this, doesn't it? Well, that's interesting. There's a way of now proving this work here in a completely different way using what's called convexity analysis. And I'll just tell you the answer. If you're familiar with convexity analysis, fine. If you're not, you're not. Okay. The density matrices form what's called a convex set of operators. This is a convex function of a convex set. There's a theorem that's been known for 100 years in mathematics that a convex function of a convex set has no traps in it. They don't use that language in mathematics, but I'm translating it for you. So the mathematics behind this proof based on convexity analysis was known in the mathematics community long before quantum mechanics. If you marry that with this structure, and what I just told you immediately follows, but it's a very different proof than this. But it also extends to classical mechanics then, because classical mechanics has the same structure. And I don't feel 100% comfortable with this myself here, because I go over to my engineering colleagues who live in the classical world, and first of all, I asked them about this when we first did this, and God, one thing I told you, you've keyed on to this quickly, that there's an infinite number of solutions. One of my graduate students presented his general's exam, and one of the faculty members was a control engineer, a very good control engineer. And she stopped him in the middle of his exam and said, "Why do you care if there's multiple solutions?" And I was shocked. All they wanted was a answer. They didn't want to know what all the possible answers were. And we have a different perspective. There's only one, and I'm not an expert on classical control theory, but as far as I know, there's only one. Well, I've given talks in meetings, in engineering meetings with classical control. I have found only one classical mathematical control engineer who's looked at the analog of this in classical mechanics and understands the principles involved, but other people are not aware of it. So, okay, suppose we're right here about this classically. What are the consequences of that? And we think they're very important, and they extend beyond this domain of coherence issues. And what are the implications? They're very important. I mean, we see, I'm sticking my neck out, but we see sort of a continuum of, I'm not saying anything about, I'm not saying about classical dynamics. Classical dynamics looks very different than quantum dynamics. We're talking about the topology of climbing up to solutions. That's it. And it says if you're trying to figure out the controls for a classical system and a quantum system in terms of the effort involved, it's basically the same. And that says important things about trying to make a device which is partly classical, partly quantum. It says things about chemistry, maybe biology, where there's no coherence issues involved. So we think the consequences of this go actually way beyond the laser game here. And maybe the laser game is the irrelevant part of the story, in fact. But that's where this started. It's a great question.
But the engineering really believes that there is no traps in the...
They don't, I don't...
They don't see that.
Like I'll give you an example of this. I went to a meeting, related to that, I went to a meeting where people were designing dielectrics to do electromagnetic scattering. It was a plane. The electric field vector was pointing up. It was the electric field satisfying Maxwell's equations, and it was stationary. Of course, the stationary Maxwell equation in one dimension is identical to Schrodinger's equation. There's no time in this problem. So speaker after speaker stood up, and they had this problem. They were moving around 50, the controls were constrained to 50 little dielectric disks. They move around in this two-dimensional space, 50 disks. They target, they were given this charge by somebody funding this, and I was just listening to it. They had to create some crazy scattering pattern as a target. Every speaker that got up there nailed it. They all got 99%, every single one. So privately, I asked them, why did it work for you? Oh, we have a great algorithm. Everybody had a great algorithm. And they were all local algorithms. They're moving around disks in 50 dimensions. I mean, how can that be? You know, and that's what originally led us to analyze this. I mean, you can't be lucky every single time here. And so that's, you know, is that quantum mechanics? Is it classical mechanics? That's a perspective issue. So we had a great discussion when you stepped out of the room, Vanderlei. So let me go on a little bit if you guys want to hear it. So let me take this to at least it makes a prediction we can measure here. So come back to the state-to-state problem, pi to f. What I just showed you, I'm not going to go through the details of this, reduces down to the following. So you climb up to the top, maximize the probability of going from state I to f, and turns out you can show the Hessian there has at most 2n minus 2 non-zero eigenvalues. And in fact, you can prove that the bottom, that's at the top of the landscape, at the bottom there's only at most 2 non-zero eigenvalues off the bottom. So that says you climb to the top, look down, if you have n levels, there's no more than 2n minus 2 ways off. At the bottom, there's only up to 2 ways off the bottom. Pure number, it makes a prediction, a pure number. It has nothing to do with the dipole matrix elements or the H-naught spectrum. So is this true? So we did this experiment with rubidium. It's true there are fine structure levels in here, but we can't resolve them within the width of our pulse shaper pixels. So this looks like a 4-level system. We start down here, we run the iterative algorithm. These transitions are within the bandwidth of the pulse shaper we have at around 700 and 800 nanometers, 800 nanometers. We climb up to the top. We get up there. We then peck away at the top statistically. So we measured the Hessian, took 20,000 pecks using sampling algorithm. The Hessian is, you can't read the numbers, it's 80 pixels by 80 in this case. And so this is actually the discretized Hessian that was measured at the top, and there's an analogous picture at the bottom. So the theory says this is a 4-level system. 2n minus 2 is 6. You can stare at that, and I challenge you to diagonalize that matrix and tell me how many eigenvalues it has in your head. We measured that in the laboratory, and we did diagonalize it, and what you see is the top. So there, this is the spectrum. There's 0. Count.
Nice symmetry in that
Pardon?
picture. Right?
It's very, because it has to be, because it's a real symmetric matrix.
Okay.
The Hessian's always real symmetric. Count. Their eigenvalues are negative. 1, 2, 3, 4, 5, 6. Exactly 6. The theory says up to 2n minus 2, up to 6, where we see 6 within some noise. The bottom is down here. There's 0. How many eigenvalues? 1, 2. I mean, there can be no accident. Out of all that mathematics, 2 pure numbers are predicted. We go in the lab, we measured it. This is what we see. We think this is very, very good empirical evidence that the theory behind this is correct. Now note, as I said, we're in 80 dimensions. I think it's 80. Yeah, 80 dimensions. 80 minus 6, there are 74 zero eigenvalues. There are 74 directions you can go in and change the control field. Nothing happens here at the top. At the bottom, unfortunately, there are 78 directions. If you're at the bottom, you won't get off the bottom. So we have the eigenvectors. Is what I just said true? So here are the 6 we got the 6 eigenvectors at the top, plus I picked randomly one of the eigenvectors of 0 eigenvalue. The number here just took a given eigenvector and multiplied it by this constant. So we're moving in the direction of the field dictated by these vectors. You'll see what happens here with the top. If we move in the direction associated with any of these 6, we come off, as we should. If you pick one of the random directions that have 0 eigenvalue, it's enormously flat. Why it peels off, of course, that vector is locally only satisfied. If you want to drive across, you move in this direction and you stop and remeasure the Hessian again, and then drive again and do it again and again. If you go to the bottom, there are the 2 eigenvectors. We move along those directions, you come off the bottom immediately. If you pick one of the eigenvector with a 0 eigenvalue, you move in that direction, you stay there. And it does do what one says. So, okay, a workhorse we look at in the lab is second harmonic or 2-photon processes. We beat the death out of these things because they're easy to do, and we can do some theory behind this with some reliability, and we can look, at least with special circumstances, at the landscape, actually see it. So it turns out if you use polynomial phase, so the controls are actually the coefficients in a polynomial, and you go out to 4th order with it, that's enough to capture the essence of the landscape, and you can argue that the topology doesn't change as a result of this. So we do second harmonic generation, and this is a filtered second harmonic signal. That means we climb up to the top, 2 photons of 800, and we filter the signal coming out. It's in some narrow bandwidth. That's what we record. That's the yield here. And there are the 2 coefficients, because it turns out the other coefficient by symmetry is gone. This is a real laboratory landscape, and this shocked us. Because if I told you to shut your eyes, and I told you we have a landscape, it's in 2 dimensions, and it has no traps in it, I think most people would say, well, it looks kind of like a Gaussian. Well, this looks like a Gaussian, and you put your fingers around it and twisted them. And if in this simple problem, the people think they understand is this is what this landscape looks like, my God, what does it look like in 300 dimensions in more serious problems? And this already shows something that really pauses about making intuitive guesses at controls. If you're in the right curvilinear coordinate system, the right superposition of the controls, you'll follow a path that takes you right up to the top. If you're not, you're going to send out a spy on the landscape, such as this trajectory, and the spy is going to report back, God, there's a lot of traps and hills and valleys, but it's a false statement having to do with the constraint on the controls. And the message from this is unconstrain the controls. You're much better off letting the controls be more flexible, work in higher dimensions, and follow your nose. Climb up and follow your nose. Okay?
Am I seeing right? But it seems to me that this landscape, it's like many saddles.
They're not saddles because
Kind of.
no. That only happens if you constrain yourself. Those are false traps. Is if you're at any point here, there's always a way up.
Yeah, but if I have a saddle this way,
Oh, so, okay. There are no.
another saddle. So
These
I
are not.
always have a way up.
This landscape has no saddles. It turns out a saddle would be one where there's the Hessian at that critical point has both positive and negative and likely 0 eigenvalues too. It has to have both. A saddle's not a trap. Any noise will.
No, but you always have a way up.
That's correct. There's always a way up.
So this is like half a saddle.
You can't. Slicing is dangerous because taking a. So look, if I what I'm telling you, go to the. All right, go to the Rocky Mountains. Of course, the Rocky Mountains have saddles and traps in it. If I give you a Jeep and allow you to drive anywhere and you can turn the steering wheel any way you want, you can climb anywhere you want. If I give you the car and you can only turn the steering wheel 2 degrees to the right and 5 degrees to the left, you're going to take some arduous trajectory, which is a false representation of what the actual topology looks like.
Suppose I have a very ideal Gaussian mountain.
Mm-hmm.
I start to drink water at the top.
Right,
Water always goes down. And then I start to make those very strange bets.
right.
But there is no accumulation of water. That's how it looks like.
That's correct. Well, that's what it looks like here. So we saw this, and if you went.
That's what it looked like always, because that's the only way of always find a way to going up.
All right, so yes and no. So I told Aunt Vanderlei yesterday, in the larger context of the question you asked, we call the result behind this the feel-good theorem. It says there's always a way up from wherever you start. It may be an arduous path, but there's always a way up. You will get stuck if, in fact, you can over-constrain the controls. Now, to what degree is over-constraining, we don't know. That's a highly problem-dependent question. What appears from the laboratory evidence and the calculations, all calculations are constrained. You don't have an infinite number of variables on the computer either. In the laboratory, let me make a mathematical statement that no one ever questions me about, because I've been hammering to you folks that we have 500 variables in the lab. Sounds like a large number. The theory behind this requires, the proof requires having an infinite number of variables. Well, the gap between infinity and 500 is a hell of a lot larger than 0 and 500. The evidence is you go into the laboratory and you make even a half reasonable choice of the controls. You know, if the molecule or the quantum system has spectral lines over here, we'll just kind of put the laser field in the general vicinity of that. That's enough. And if you can't quite get there, put it over here and jack the intensity enough up, it'll warp, dynamically warp the energy levels, and you'll still get there. So we get away with murder here in the laboratory. And that was one of the arguments this wasn't going to work, because all these experiments use the same laser. No matter what the quantum system is, you use the same laser. If you're a spectroscopist, you say you're going to use the same instrument to take the spectrum of everything. You know, it isn't going to work. But this isn't spectroscopy. In fact, we're warping the system. So we don't fully understand. Tucson and I have been going back and forth about this issue of how do we assess when we are dealing with this kind of problem when we can't look at it in 2 dimensions. We go from an infinite number to 500. How smart can we go? Can we go down to 3 if we pick them judiciously? How do you pick them judiciously? You know, maybe there's not going to be an answer to those questions, and the answer is go do the experiment, get what you get. We don't know at this point, okay? So here's the statement. I said you this before. So here shows laboratory trajectories climbing to the top from different initial points. You can measure is a real laboratory data, second harmonic. You can measure the path length versus Euclidean distance. The ratio is not even is less than 1. I mean, certainly less than 2. It's very low. You look up, there's a solution. Look up from here, there's a solution. It really is easy to do this. Multiplicity of solutions, we've talked about this. And in a sense, the answer of why this is true is we start at a point, we're asking for a number at the end. It's not a shocking surprise, in some sense, that there's an infinite number of pathways from here to there. And is it true? We go back to the Flavin experiment, and I'm almost through here, incidentally. We did this experiment. We run it today. You push the button, 20 minutes later, we get a control field. We wait 2 weeks, and we dial that control field in 2 weeks later. We've got now a good laser system. Within experimental noise, we get the same result. But if tomorrow we start the experiment all over again and push the button, generally we find a completely different field. Gives us a reasonably the same answer. And that's exactly what I'm showing you here. These are laser pulse shapes. They're spectrograms, frequency versus time. This is the analog of a musical score. You know, when you play a musical instrument, like piano, you're reading across here, there's frequency versus time. This complex spectral and complicated chirp structure is speaking to the dynamics of the system. We don't fully understand that. But these different controls give, within noise, the same solution. In fact, there are a menu of them. They're much larger than this. And so we argue mathematically these are very likely continuously morphable, but we haven't seen that. They look discrete here.
Well, obviously, I was already going to ask this. Because your target is just a real number, that's probably the reason, no? Because if your target is specific wave function, of course you can have 2 vastly different wave functions
Yes, and so the closest to that is quantum information sciences. So here we are after a very gentle, kind, simple thing. Take the trace, which is like an integral, over the density matrix times the observable operator, get one number. Now, however, all the arguments people gave against this, if you look at it from this point of view, it doesn't sound very demanding, and in the end, it's not. You come to quantum information sciences, they want the whole damn unitary transformation. Not just one number, they want every single matrix element to be right. And that's asking for trouble. So we have analyzed the landscape of that problem. It also has no traps. It has saddles, it has no traps, but the topology story seems to be a lot worse. The top is not as friendly, it's not as robust to noise, and that spells real trouble for practical problems. And I'm saying nothing about, what do you make it out of and decoherence issues. It's another, well, it's related to decoherence issues, but asking for more is asking for trouble in this game, although inherently there are no traps in these problems. But asking to hit the trace of rho O, in the end, after all said and done, it's not asking a lot, but it's, the details count as to what actually comes out, and what we see counting at the topological structure at the top, you have to look at the details of it. But of course, that's the beauty of this in the final analysis. However messy and crazy quantum mechanics sounds, most real questions people ask are not actually that demanding in the end. And it comes with some inherent, very attractive properties associated with robustness. So, where is this going? I showed you this list the other day, and I'll be happy to leave this with you guys. So I count, and I don't know whether this is an accurate list or not, but were it not for X, then none of this would work. And the reasons range from putting it, frankly, on a firm mathematical footing. This was not recognized as a control problem until around 1990, 1988. And until that time, people looked at this problem, physicists and chemists mainly, looked at this problem as the usual science is looked at by intuition. And this problem defied intuition. You can see why. And when this was finally recognized as a control problem, things started to open up. And what it first led to was exactly what are the nature of the laser resources needed. People were guessing. And they were guessing at this, which is exactly the wrong thing to guess at. And so the first thing theory did is it pointed to the fact that we needed coherent broad bandwidth resources. And in fact, when the theory showed that, those sources did not exist. But they came immediately afterwards by coincidence in the telecommunications industry. But there are many reasons for this working now, not the least of which, where would we be without the titanium sapphire laser? I mean, it's a coincidence it's here. But I'd also like to believe that 10 years from now, or whatever number of years from now, people will look back and laugh that we worked with this laser system. It's terrible. It doesn't operate in a regime that's generally very useful for interacting with most chunks of matter. It's narrow bandwidth, we don't like it. But there's many reasons here, some of which I've talked about. So where is this going? Let me just finish up with a couple views and we'll be through. We already have talked about this point in a general way. So what are the controls? We've been talking about laser fields, the electric field and light, but we've already talked about it's not the only thing. The theory behind this landscape story says what's behind it is Hamiltonian manipulation. And there's nothing in this that says we have to manipulate the Hamiltonian through the electric field. We've got the stockroom to pick amongst as well, choose the bottles. And the ultimate here is to shop amongst the photonic and material reagents, and this ultimately leads to the following cartoon. So here's our laser lab. You guys understand that. And all the stuff going on in Vanderlei's world here, my God, you understand everything anyway. This is a cartoon, it's not a real picture, of some guy sitting in a typical chemistry or biochemistry lab. And if you could see it better, the question is here, what's the difference? In fact, we argue there isn't any difference. This uses photonic reagents, this uses material reagents. In fact, they're really the same thing at some level. And you could combine them together if you're making electro-optic materials, or forget the lasers. If you're doing chemistry or materials engineering, operate completely over here. And there's a lot of evidence, I'm not showing you this here, there's a whole other talk, that this world, in terms of the whole story I told you about, looks exactly like this world. It really isn't any different. So that's the end. And the bottom line is everything's open, we think. We don't understand everything, but everything seems open. Other questions?
Let's first.
Okay. First of all, let me thank you, although you folks, some of you asked very perceptive and interesting questions. Thank you for letting me take the time to finish the whole story. I've talked about this many, many times, including last week somewhere, and most times they won't let me finish the story. And so there we are. But I'm happy to entertain other questions. So great questions.
Oh, just one simple question.
I've always heard that. One simple question.
Yeah, this is, of course, when you say about many degrees of freedom, people think about life, bio stuff.
Right.
And yesterday you gave a kind of flavor that maybe this is the kind of thing that may be going on in some of the mechanisms that will take forever for evolution. But because of that kind of argument, it may take shorter. And that will explain some of the features of the evolution of life.
Okay, so
I mean, is that the case?
I believe that's
Has
true.
hope for that?
I believe that's true. So, I mean, we're not the first people to think of this issue. First of all, we follow our nose around here. This started, with quantum mechanics. We've been working on this stuff for over 20 years now. And this question of why this works finally was gnawing on us for years, and we finally started wrestling with it in detail started 6 years ago. And, I sit in the chemistry department, and I gave a talk as a forerunner to that question, Banner, I gave a talk to the juniors in the department last fall titled, "Why is Chemistry Easy?" And chemistry is shockingly easy. And in fact, I'll show you let me get out. How do I get out of this thing here? So let me get out of it, and I'll show you just the beginning of something. Okay. So why does chemistry work? So here's the introduction. I'm not going to go any further with it because we'll be here all afternoon. I'll read that to you. It says, "I'm on the verge of a major breakthrough, but I'm also at that point where physics leaves off and chemistry begins, so I'll have to drop the whole thing." I think that physicists, and this is just a belief, you can tell me otherwise, know enough about mathematics generally, know there's something odd about chemistry. Chemists, you come to them, you say, "Make this stuff." And God, it looks like a black art. The stockroom, in fact, the stockroom is infinitely big. Denumerably, if not continuously infinitely big. There's something wrong about this problem. So what I told the juniors is, they take 10 chemistry courses. They get so smart from taking 10 chemistry courses, you ask them to make anything, and don't ask a ridiculous question like, make carbon with valency 18. I mean, you have to have a well-posed question, a controllable problem.
Make aspirin.
Pardon?
Make aspirin.
Make aspirin, okay, we can do that. It works. How many visits to the stockroom does it take? Very little. Chemists take it for granted. They don't question the statement. But it's shocking. And so here's a quote from a Nobel Prize winner, 1998, I believe. "Chemistry is all about getting lucky. I think physicists think that's true." Is it true? That's the question. Is that what chemistry is about? So I'm not going to show you this because it's a whole talk unto itself. It goes through exactly the same arguments, and we looked in the chemical literature. There's evidence all over the place in the chemical literature. I mean, quantitative evidence. They just took this sort of anecdotally that chemistry works, but there's quantitative evidence all over in the chemical literature that it operates under the same principles. These landscapes have been measured in many chemical cases. And 90% of them that have been measured, hundreds of them in the literature, are trap-free. So this led us to, okay, what's the consequences behind chemistry and material science as well? And it leads to biology. And I don't mean chemical reactions in biology. That's part of this story too, but evolution. And again, we didn't think of this question. Evolutionary biologists have been wrestling with this for 100 years. And the question is, how am I standing here talking to you after 1 billion years of evolution? It's not reasonable. For the same reason this isn't reasonable. As you can't do, Mother Nature is a stochastic process guided by some cost function. And biologists are very fuzzy about what the cost function is, but all right, you often pick the growth rate of a species. Good, high growth rate's good. Accept the statement. It is not reasonable, given the rate of mutations that people argue have occurred, that 1 billion years is enough time for me to evolve to talk to you here. So what's going on? So evolutionary biologists talk about landscapes in exactly the same way we talk about them, except they get them by going like this. They think it looks like something. There's not a shred of theory behind it. They postulate what they look like. And we argue, all of classical mechanics, not quantum mechanics, really, that the landscape is in fact trap-free in biology, in evolution. And there's a lot of evidence, not from the evolutionary record, but from laboratory experiments in evolution over the last 30 years.
Because there are many different species.
That's multiples. Look, it's a complicated story.
Are flies going to evolve into human beings?
What we have shown, and I'm not an evolutionary biologist, so I have to be careful what I know and don't know. So we confined this to one species, just like we take a rubidium in the laboratory. We picked a bottle off the shelf. So we pick E. coli, pick one bacterium, not every monkeys and bacteria and everything else. Pick one species. Go into the laboratory, and we don't do these experiments, but people do this. They do evolutionary experiments on bacteria, and they can go through one generation in a day. And there's people who have been doing this for 20 years. You can add up the number of generations. They're very, very large. And they make changes. They move across the top, and they move down. And they come back up on the landscape. Those experiments are consistent with this theory. There are also viral experiments. Viruses, unfortunately, as we know from the flu, mutated at a prodigious rate because their genomes are small. Most of those experiments that are done in that area are also consistent with this too. So other than evolution, which is just an interesting subject, the practical side of that is doing engineering at the molecular scale, at the gene level, to engineer proteins, for example. And there's a literature there, and people say this in that literature. They observe that, my God, they have a protein of some gargantuan size, and they do mutations at the gene level, and they observe it took 10,000 experiments or 50,000 out of an astronomical number, and they get it. We argue the reason is exactly the same thing, because of the same landscape. So it has practical consequences as well. So I'm, of course, sticking my neck out by saying this, but there it is. Other questions?
Thank you again, and Professor is going to stay until tomorrow, so if any of you are shy to come talk, you can go private to his room.
They're not shy here. No, they had great questions. I really appreciate it.
Okay, so let's thank again. E vai ter, nós filmamos, então você vai poder fazer o download.
I was thinking about what Marcel asked.
Simplificado,